So thanks to the organisers for giving me the opportunity to talk to you. So I'm going to talk about three works that I've done recently, trying to understand various aspects of the radial acceleration relation from a data analysis point of view, in collaboration with these two people here. So Stacey has mostly spared me the task of introducing the RAR. I'll do that just briefly, and then I'll describe my three approaches. So the first is to optimize the nuisance parameters of galaxies that the coordinates of the RAR depend on in order to reveal the intrinsic, or what I call the underlying, radial acceleration relation. The second is to use a technique called symbolic regression to try to understand the functional form of the radial acceleration relation, and specifically whether or with what probability it satisfies the Mondian limits of a Newtonian regime, the MOND regime. And then the third is to ask whether the RAR can be understood as the fundamental correlation of late-time galaxy dynamics. So I'll lay out some criteria for that to be the case, and then assess them quantitatively using machine learning techniques. Okay, so here is the radial acceleration relation. So I'll use the SPARC dataset that Stacey and Federico compiled. This is a slightly different view than Stacey presented. He showed a kind of utilized bin version. This is literally all the points of roughly 150 galaxies on the plane of gbar, so the acceleration sourced by the baryons alone, and gobs, the total dynamical acceleration. So in lambda CDM, this implies that at high acceleration, dark matter is dynamically insignificant, whereas at low acceleration, it becomes important in this way that seems to be strongly correlated with the baryons, and the origin of that is rather mysterious. In MOND, it follows directly from the basic tenets of the theory, and essentially describes the prediction of MOND in a kind of statistically averaged sense for the in-disk dynamics of galaxies. So in MOND, you have a Newtonian regime at high acceleration where Newtonian mechanics is recovered. You have a deep MOND regime where the logarithmic slope tends to a half. And going between the two, you have some kind of interpolating function, of which these are the three classics. So one subtlety that's relevant is that in the presence of a strong external field, you have this thing called the external field effect, which is the way in which MOND breaks the strong equivalence principle, and that causes the relation to tend back to the Newtonian slope 1 prediction at very low baryonic accelerations. Okay, so here are the three things that my three analyses are targeting. So first, the large observed scatter in these points, the large size of the error bar, are due mainly to uncertainties in the properties of the galaxies as a whole, rather than individual uncertainties in the gobs and gbar points within the rotation. And that introduces correlated deviations from the mean RAR. So all the points in the rotation curve of this particular galaxy, for example, deviate due to the properties of that galaxy as a whole not being as expected a priori in the SPARC error. So my first analysis develops the statistical methods to treat that properly. Second, all the functions that have been used to fit the RAR previously have basically been inspired by MOND. So they have, by construction, the MOND limits. So the second thing I want to know is, are these the optimal functional descriptions of the data, or might there be better ones? And then finally, these residuals of the radial acceleration relation, are they correlated with anything? Is gbar the best variable for predicting gobs? And is gobs the best dynamical quantity, the dynamical quantity that's most strongly correlated with baryons? That's what my third analysis. Okay, so the coordinates of the RAR, gbar and gobs, aren't measured directly, but they depend on the photometry and rotation curves of galaxies. And those, they depend in particular on the galaxies' luminosities, their mass-to-light ratios, their inclinations, and their distances. And each of those things have informative priors from previous measurements. So what's normally done in creating RAR that I show here, for example, is to fix those parameters to their maximum a priori values, and then propagate their uncertainties as statistical uncertainties in gbar and gobs. That assumes that those uncertainties are Gaussian and that they're uncorrelated between data points. But that's problematic because variations in these quantities actually introduce correlated deviations on the RAR plane. Whereas if you propagate them statistically, then that's tantamount to assuming that if the mass to light ratio of a galaxy fluctuates up, for example, that could cause gbar to fluctuate up at one point but down at the next. That's clearly unrealistic. If mass to light ratio fluctuates up, then gbar should fluctuate up for all points for that galaxy. So the proper way to do this analysis is to infer all of these nuisance parameters of the galaxies simultaneously with the parameters of the RAR itself that you're trying to infer. So that will naturally propagate those uncertainties as systematics in the RAR, and it will map out the full degeneracies between those parameters and the properties of the RAR. So I'll assume here that the RAR is described by a simple interpolating function. It doesn't matter much what exactly you choose. That has a single free parameter, A0, plus an intrinsic scatter. So if I want to do this full analysis then, if I had 147 galaxies, of which 31 have important voltages, I need in total 768 parameters to be inferred simultaneously. So all of these quantities here for each galaxy, plus A0 and the intrinsic scatter in RAR. That's a very difficult thing to do for most Markov chain Monte Carlo samplers. Turns out it's fairly straightforward with a more advanced technique called Hamiltonian Monte Carlo. So the idea here is to simply plug this data into an HNC sample using the SPARC error model to determine the priors on these galaxy-wide parameters, and then infer all these things simultaneously. So what I'm showing in this plot is taking the best fit values for these galaxy nuisance parameters and using them to transform gbar and gobs according to these formulae to uncover essentially the RAR that underlies the uncertainties in these galaxy parameters. And that's shown in the blue points here. And I've overplotted them on the original prior RAR, which is shown in grey. So you can see that the residual, the sort of correlated deviations from the RAR go away when you do this. And all that's left of the statistical uncertainty is the point-by-point uncertainty on VOBs. So I've tried a few different modeling assumptions for how you treat the priors, the external field effect, and so on, but the results are fairly stable. So as we know, A0 is around 1.2 meters per second squared. But what's interesting is that when you use this more correct way of treating systematics, the intrinsic scatter in the RAR drops from around 0.1 dex, as it is in Stacy and Federico's analysis, to 0.034 dex, which is around 8%. That makes it obviously an incredibly tight scaling relation. It's actually possible to reduce those uncertainties or that scatter even to zero with plausible additional uncertainties due to variation in, for example, the thickness of the baryonic disk. Or it could, of course, be due to deviations, for example, from non-circularity in modified inertia interpretation of So what I show on this plot here is the distribution of fractional uncertainties in these galaxy parameters in the prior, in orange, and at the best fit point of the posterior in blue. So you can see, for example, that if I look at the galaxy distances, this bump here in the prior corresponds to distances that have been estimated just from the Hubble flow, which were given a fairly large fractional uncertainty. If you require that these galaxies lie on RAR, then you get much more precise measurement of their distance and of their other parameters as well. So, for example, the underlying RAR gives you about a 10% redshift-independent measure of distance, which is roughly twice as good as the classic Tully-Fisher method. Okay, so that's it for my first analysis. Second, I want to know what the functional form of the radial acceleration relation is. So, for example, are the interpolating functions that people have been using to fit the RAR in the past, are they the best descriptions of the data? and more generally, do the best descriptions, whatever they are, satisfy the MOND limits, which means they could be considered new interpreted functions. So methods for optimizing the functional form of a data set, as opposed to simply optimizing the numerical values of free parameters that appear in a function, go by the name of symbolic regression. This is a fairly new field in machine learning, and my collaborators and I have been going down a rabbit hole of trying to do this properly, which I'll spare you the details of, except so far as to say that we developed a new method for symbolic regression called exhaustive symbolic regression, which essentially creates an efficient algorithm for generating all possible functions made of some basis set of operators, which I'll take as these for the moment, up to some maximum complexity of function. So it generates all possible functions and then scores the functions by asking how accurate they are on the data, so what is the likelihood of the data given the function, and also how simple the functions are, because you want to prefer simpler functions, you want to avoid overfitting. And so those two criteria of accuracy and simplicity are combined in this information theoretic principle called the minimum description length principle, which basically says that the best function is the one that allows you to communicate the function and the data with the help of the function in the fewest bits. So I'll spare you all the details of this, but if you're interested in symbolic regression in general, then I encourage you to have a look at our papers, and all our code and data are also public. Okay, but to apply this to the RAR, so I have up here the SPARC data again, and what I'm doing is I'm overplotting the 20 best functions that have been identified by ESR, color-coded by their probability of being correct as measured by their description. So darker is better and lighter is worse. These panels show exactly the same thing, but on mock data generated according to the RAR interpolating function or the simple interpolating function, including the external factor. These plots over here show the description length and accuracy or likelihood of the best function found at each complexity, compared to the interpolating functions up here and the double power law as a simple foil for the MOND function. So what you can see from this is that ESR discovers functions that are both more accurate and simpler than the interpolating function. And that's actually true even on mock data that have explicitly been generated according to MOND. So for example, this data set here was generated according to the RAR-IF, which is this star here. But ESR has found simpler and more accurate functional fits, even at lower complexity than the one used to generate. And the best function in each of these cases is shown now. So what that tells us is that there are better functional descriptions of the data than the MOND interpolating functions. You can see that the best functions don't really have the MOND limits, so they have the Newtonian limit fairly well, but the deep MOND limit not really. Instead, gobs prefers to go to a constant at low gbar rather than having a logarithmic slope over half. So then this plot shows in more detail the logarithmic slopes of the best functions, since that's what I'm using as the criterion for whether a function is Mondian or not. So what I have here is for each of the three data sets, for each of the top 10 functions, I calculate the logarithmic slope as g bar goes to infinity in red, as g bar goes to 0 in blue, and at the highest and lowest g bar values of the data in magenta and cyan. And in cases where the logarithmic slope depends on free parameters of the function, then I run an MCMC for each function separately and show the 95% confidence limit on the slope as a band rather than a point. So what you can see, again, is that most of the best functions have a Newtonian limit, so a limiting logarithmic slope, high acceleration of 1, but they don't really have a deep MOND limit. They instead prefer the acceleration of gobs to go to a constant. And that's true, again, even on the mock data. So the RAR-IF data explicitly has a phase-10 slope of 0.5, but you tend to recover 0 instead. And what that means is that the quality and quantity of the data isn't really sufficient to be able to pick out that the data is generated by MOND, even if it is. So the advantage of using the minimum description length principle is that it prefers simpler functions in cases where the data is limited. And simpler functions in this case tend to be those that tend to a constant rather than the logarithmic slope. So this test seems to be inconclusive. Okay, on to my final topic. So here I want to know whether the RAR can be considered in some sense the fundamental correlation of the radial dynamics of late-type galaxies. So I have these 4 criteria for what it would mean for any relation like the RAR to be fundamental. So it must have no residual correlations with any other variable, because if it did, then you could make a tighter relation by including that variable. It has to be the tightest projection of galaxies' dynamical parameter space. It has to be able to account on its own for all the other possible correlations. And it has to be unique in that no partially independent correlation also possesses those properties. So I'll now work through these things for the RAR. So starting off with the residual correlations. So what I show here is the partial correlation coefficient of gobs at fixed gbar with all the other galaxy variables in the SPARC dataset, plus the external field estimated separately. So the correlation coefficients in the data are shown by the red crosses. The blue violins show the results on mock data that are SPARC-like in every way, but with dynamics explicitly generated only through the RAR. So you can see that the red crosses look like typical draws from a blue distribution. They don't seem to have any significant residual correlation with anything else. In case you're worried that maybe those correlations could be washed out by the uncertainties in the data or the heterogeneity of the galaxies in SPARC, I'm also showing mock data in green that are generated according to what I'll show to be the second strongest correlation in the SPARC dataset, which happens to be between the observed jerk, gobs, and the total surface brightness of the galaxy. You can see that in that case there are significant residual correlations that disagree with the data. So this shows that the data could plausibly have been generated from the RAR alone, but not from the second strongest correlation. So another way to get at this question is to ask whether your prediction of gobs can be improved by folding in variables besides gbar. So what I'm doing here is I'm training a nonlinear machine learning model called an extra trees regressor to predict gobs, training on one or more baryonic properties. So on the diagonal here, I feed the regressor just one of these properties, and on the off diagonal, I feed it a pair of properties. And I'm measuring the loss in its prediction of gobs. So you can see that gbar alone gives you the best prediction of gobs. If you give it any second quantity as well, it doesn't make the prediction any better. And in fact, typically it makes it worse because you're simply confusing the regressor with irrelevant information. Okay, so there appear to be no residual correlations. So that's essentially established that all the information on gobs is contained in gbar. But now I want to go further and ask whether gobs is the optimum target. Is that the dynamical quantity that's best correlated with the baryonic properties of the galaxy? And to do that, I develop or I generate this generic dynamical variable, v obs to the alpha over r to the beta, parameterize it with this angle theta, since d is equally predictable as d to some power, so within 1 degree of freedom. Then retrain my extra trees regressor, but now to predict d as a function of theta based on baryonic properties. So this shows the result. I'm taking here just the 3 baryonic properties that turn out to be most relevant. So gbar, the surface brightness of the galaxy, and total luminosity, 3.6. So you can see that the trough here, which is the quantity that can be predicted best by these dynamic variables, is at exactly the theta value corresponding to gobs, which is arctan of the half, and it is predicted best by gbar. Also, gbar, the predictivity of gbar peaks at exactly gobs, as you would expect from these correlations being generated entirely by the RAR. So the evidence gets stronger when you look at mock data, again, which have the RAR as the only dynamical correlation. So that's shown in dashed with the residuals from the data shown at the bottom. So you can see that, unsurprisingly, if you generate data only using the RAR, you recover the fact that there is a strong correlation at the RAR. But what's surprising is that you actually recover all the trends in this data set as well. So for example, the second strongest correlation between sigma and the jerk also follows just from the RAR plus non-dynamical correlations that are present in the SPARC data set. But the converse isn't true. If you assume that the sigma J-obs relation is fundamental and generate your mock data according to that, you don't recover, for example, the trough at the RAR. You instead get a much weaker correlation between gbar and gobs. So that shows that for all intents and purposes, this data looks like it's been generated solely by means of the RAR. And if even the second strongest correlation between surface brightness and J-obs can't predict these generic correlations, then we can be confident that no other correlation will be able to. So that ticks off the other 3 bullet points for the fundamentality of the RAR for radial galaxy dynamics. Okay, so that's it. I'll just leave you with my conclusions. So I've shown that by optimizing the galaxy parameters that are relevant for gbar and gobs, you uncover the underlying RAR, which is an intrinsic scatter of just 8% and shows no evidence of deviation from simple interpolating functions. I've shown that symbolic regression, I've shown a search for the best functional description of the data using symbolic regression, which seems to indicate that the data quality and quantity isn't sufficient at the moment for establishing definitively whether it has Mondian limits. And I've shown that the RAR seems to have no significant residual correlation with any other variable and is alone capable of generating all the radial correlations that are present in the data, which means we can call it the fundamental relation of things like that. And that's it.
I can start. So, one comment is that we could probably do better if you added the information for recleansing.
Yeah, that's definitely would be interesting.
The other being that, okay, so if we concentrate on the low acceleration part of the area, then it picks up contributions from 2 regions. So one is like the sort of flattish asymptotic part of any galaxy, even high acceleration galaxies. The other is from the inner parts of low acceleration galaxies. Now, it's important to realize this because it means that the quality and the result of the area will depend much on your sampling, whether you have many low surface brightness galaxies in it. You could get the area just from high acceleration galaxies. And this reflects on claims, I think, that lambda CDM can also reproduce the area in the following sense, that it's enough that you have sort of a flattish part of asymptotic rotation plus an approximate Talley-Fisher relation. Doesn't have to be a power of 4. It could be power, let's say, between 3.5 and 4.5 to reproduce the low acceleration part of the. So it's very important how you sample the area. So does your analysis actually? It's even important, with a given galaxy, how many points you pick up from the flattish part or from the Newtonian part.
Yeah, so I think that is included in some sense in this because all these various galaxy properties that are also here in SPARC here, in combination with one another, tell you about whether you're in the outer regions of a high surface brightness galaxy or the central regions of a low surface brightness galaxy. For example, the combination of distance and sigma. So this is indeed indicating that there is no systematic discrepancy in the RAR plane between those two regions.
But it would also be interesting to see what you get if you analyze the results of lambda CDF simulations.
Yeah, totally. That's something else that I want to do at some point. The trouble is that there are many of them and they disagree with one another, so what do you choose? Yeah.
Federico Lelli from Architecture Observatory. Very nice work, Harry. I have a question about the second aspect, so the symbolic regression. So what level of data accuracy or percentage error would you need in order that to work? And related to this, have you tried a simple trick, which is using the results from the first experiment, so that you have the optimal distances, inclination, and mass to light ratio with reduced errors, and then use the symbolic regression on those data?
Yeah, good question. So for the first question, I don't know, but it's very easy to find out, because all I need to do is generate mock data with some arbitrary dynamical range, with some arbitrary uncertainties, and figure out how reliably you back out the generating function, essentially. I've not done that exercise, but it can be done. So if you're interested, we can.
And you think it's a matter of errors on individual data or statistics in general? In the sense, if I give you a sample which is 10 times larger with the same percentage error, will it improve, or you need, a smaller sample with much better data?
So I think the most important thing is the dynamical range, because I'm trying to find the slopes. So the further I can probe into those two separate parts, the better. I think that's the most important. Probably the second most important would be the uncertainties, rather than just the number of data points, because there's already quite a lot. With regard to your second question, the trouble with doing that is that that first analysis assumes a simple interpolating function. Okay, and you would get different results on the galaxy parameters if you took, say, this function and fitted around that rather than the simple. So you kind of
I understand. It was just a mock exercise to see whether in that case with better errors on the nuisance parameter you do recover, let's say, the input interpolation.
The mock example, the mock test, very easy to do, but I haven't done it.
Thank you. Guillaume Todd from the Institute of Astrophysical Analysis. So it's really interesting result, but it seems that when you take into account anyways the external field effect, you should not account to get only just a relation, but you're going to get a wider scatter, because it will depend on the location of the galaxy. If it is inside another galaxy, if it is around, completely isolated, and so on. And it seems that actually your method is able to recover that you have many flavors, at least when you do the simple EFE plus the external field effect, even with just the SPARC mock, where you don't necessarily sample the lowest part of the bionic accelerations, which is pretty interesting. And if you go back to the observed data, you can still see that you have some scatter in the observation. Well, actually, it was exactly that plot you were showing. That you can see that with your method of the symbolic regression, you can still see that you have some scatter that are predicted in the end, even with the actual data. So do you think that actually it's something that it's telling us that some of the galaxies are on different locations, some of them are isolated and so on?
Well, I'm sure Hugh is going to talk about this more in just a moment. I think there is certainly some evidence for that. Most of the time here, I've just been assuming the external field is constant across all the galaxies, just for simplicity. Although actually when I, in this final analysis, did this correlation with the external field strength here, that is a galaxy by galaxy estimate based on the large scale structure, which I estimated for Hugh's paper. So I think all three of these analyses haven't really been designed to target the EFE. They all kind of independently provide, I would say, very weak evidence for that. But Hugh will talk more about that in a second.
My question was about symbolic regression. Does it actually work only for elementary functions, or it becomes also more complicated like higher transcendental functions?
Good, so you can use whatever operators you like in symbolic regression. So this is what I have here. So just these are the basic operator sets, and then any function is built by combinations of those operators. But you could also just introduce some custom operator that would be a combination of those, and just use that as a single operator. So I didn't mention it, but what I'm calling complexity here is basically the number of times an operator, parameter, or variable appears in the function. So the sum of all those things. If you were to define your own custom operator, then you would make functions that include that operator simpler than others, right? Because you don't have to write that out in terms of what it's made of. It's just one thing. So that is basically the one degree of freedom that the user has to determine in advance what the basis set of operators is. But there's no limitations to it. So whatever operator you think might be useful in your problem, you can just put that in.
The last question, my function.
Oh, yes, sorry. My question is, my comment is, okay, very, very beautiful work. I take it as an independent evidence that, after MOND made these predictions, there seems to be more information in the data than previously understood by. So I think it's a confirmation that there is some miraculous things MOND is capturing correctly. On furthering some of the things you're doing here, I wonder whether that implicit, that regression method, could it be done through an intermediate variable such that both gobs and gbar could be function of something else through these algebraic relation? Hence, they are implicit functions of each other. Maybe this relaxes some of the things. You do? Just an idea?
Yeah. Yeah, that's very interesting. So basically, and actually that's sort of the motivation for the third analysis exercise, because I'm assuming here that gbar and gobs are the fundamental quantities, so the functional form you want is between those two, but you want to know kind of whether they are the optimum quantities to correlate. And that's where that machine learning exercise comes in. So you can see that it is, and that kind of justifies fitting it in that way.
I'll be very happy to work on this. Thank you.
Good.
Thank you very much.